Hey, what's up, chemistry folks? Mr. Boylan here. Today we are going to make qualitative or quantitative predictions about galvanic cells based on half-cell reactions and potentials, and analyze these cells to identify properties of the underlying redox reaction. Now, that's a pretty intense objective. We talked actually about this very same thing in the previous video, but we're looking at a little bit different aspect today. We're going to take a little time out from electrochemistry. So if we break down that content objective into a couple of points that we're going to focus on for this video, we're going to explain the concept of equilibrium, which is a pretty big concept and is something that we're going to spend an entire unit on later in the year. So we're just going to brush the surface here really quickly and sort of how it ties into your electrochemistry unit. We're going to talk about how you can calculate what's called an equilibrium constant, which is abbreviated with the symbol K. And then lastly, we're going to talk about how you can calculate what's called a reaction quotient, which is symbolized with the unit Q. So some new vocabulary here, a quick timeout from electrochemistry, but really, we're going to time ourselves right back in after we understand what's going on with equilibrium. All right, so a few quick things here. First, it's important to know that chemical reactions are actually reversible. I know a lot of times in the first year course, we don't really think about reactions happening in both directions, but they can. And as you start to see these reactions that are reversible being expressed, you're going to start to see these double-headed arrows indicating that reversibility. Now, why are we bringing this up right now in our unit of electrochemistry? Well, there are quite a few examples of these reversible reactions. A big example is the exchange of electrons in redox reactions, which is the main focus of our electrochemistry unit, which is why we're going to start talking about equilibrium. Now, when you think about a reversible reaction, or when you think about a reaction that is at equilibrium, essentially have both reactants and products present. Again, in these types of reactions, you can have both the forward and reverse reactions. So at equilibrium, you can have both your reactants and products that you have expressed in your equation. Dynamic equilibrium is then reached when the forward and reverse reactions continue at the same rate. And the concentrations of those reactants then and products are constant. Now, to give you a quick visual of sort of what's going on with equilibrium, I'm going to sort of continue to replay this reaction here, where we've got dinitrogen tetroxide gas and nitrogen dioxide gas. And notice here we got the double-headed arrow indicating the reversibility of this reaction. But right now I want you just to focus on sort of the molecular diagram of this reaction here at the bottom. Notice that at equilibrium, both the forward reaction occurs, where we form those nitrogen dioxide molecules, and the reverse, where we reform sort of that dinitrogen tetroxide molecule. So at dynamic equilibrium, we have sort of this back and forth. All right, now we'll talk a little bit more about the specifics of equilibrium once we get to the equilibrium unit, but you should know just in general that the forward reaction is favored when you have a lot of reactants to start with, and they're going to sort of move over and sort of form those products. Likewise, if you've got a lot of product in your reaction, the reverse is favored, and those products will then move to form your reactants. All right, so we're just going to play the animation that illustrates this reaction again between N2O4 and NO2. Again, it's sort of this reversible reaction, and we're going to start with pure NO2. So we're going to start with all of essentially what's written as our product here. And because we're going to start with all of this NO2, we're going to initially favor the formation of our reactant molecules there, N2O4. And as you are thinking about this reaction at the sort of macroscopic level, the N2O4 is colorless, but the NO2 is sort of a brown gas. And so as you watch this animation at the macroscopic level, you're going to be looking at this color change, but then at the microscopic or atomic level, I want you to sort of see sort of what's happening as we move back and forth between these products and reactants. So our reaction begins with pure NO2. We've got a very brown gas here and mostly NO2 molecules. As the reaction proceeds, though, that NO2 starts to form the N2O4 until we reach dynamic equilibrium. In other words, the rate of the reaction the formation of the products equals the rate of the reaction formation of your reactants. And so as you look at that sort of at your atomic level, again, it sort of looks static at the macroscopic, but at the microscopic or the atomic level, we've got this sort of dynamic back and forth. The reaction is forming the NO2 molecules and then reforming the N2O4 molecules. Again, dynamic equilibrium. All right, now what I really want you to take away from this idea of equilibrium, what we're really going to start to tie into electrochemistry is this idea of the equilibrium constant, K. And this constant just relates, it just tells us what's the relationship between the concentration of the reactant and the concentration of the products at equilibrium at a given temperature. Now, how do we determine what that equilibrium constant is? We're going to use the equilibrium constant expression K. So if we've got this sort of general reaction here, where you've got your reactants A plus B to those respective coefficients in lowercase, forming C plus D as your products, again, C and D in lowercase indicating your coefficients in that balanced chemical equation. The equilibrium constant expression K can be expressed in the following manner. Again, product molar concentrations are in the numerator, and reactant molar concentrations are in your denominator. So products to reactants, just a comparison between the two. Each concentration is raised to the power of its stoichiometric coefficients in the balanced chemical equation. And it's important to note that pure solids and pure liquids are not placed into the expression. We'll talk more about that when we get to equilibrium, but just recognize you're only going to have your aqueous solutions, your ones that you can write a concentration for, or your gases, but we'll talk more about that in equilibrium. So what does this number tell me when you solve for K? What is it going to tell me? Well, if you get a K value that is greater than 1, it's simply telling you that you've got more product formation at equilibrium. You've got a lot of product at the equilibrium point in your reaction. So if we have this general reaction here, again, reactants and products, your equilibrium constant expression is products over reactants. If K is large, that is simply telling me that I've got a lot of product at equilibrium, that product formation is favored. Conversely, if K is less than 1, then the reactant formation is favored. And again, this is just based on how we describe the equilibrium constant. Because it's products over reactants, if you have a small K value, if you've got a small equilibrium constant, it just means you've got a lot of reactants favored at equilibrium because the reactants are in your denominator. And then if K equals 1, well, that means you've got approximately the same concentration of products as you do reactants at equilibrium. And so you'll have roughly the same values in your products as you do for your reactants. So as you look at this animation that starts out with a bunch of fish in one side of your fish tank, they sort of fill up the container there and sort of swim back and forth, back and forth, back and forth. So you've got 5 fish in your reactant chamber and 5 in your product chamber once you reach equilibrium. So in that case, K would be equal to 1, where you've got essentially the same amount of product as you do reactant. But if you use the same sort of analogy when you've got sort of a giant cat at one of those reaction chambers, in this case, we'll say the reactant side, yes, there's sort of this back and forth still, but as soon as like a fish swims over, that's like, oh, there's a cat, let me get out of the way, and sort of swims back. So still this back and forth, back and forth, back and forth. But in this example, our K value would be very large or larger than 1 because we've got a lot of product in this case and not a whole lot of reactant. All right, and then sort of lastly here, big thing to take away from equilibrium is this idea of called the reaction quotient, Q. And the reaction quotient is just a measure, again, of the proportions of the products to reactants. But instead of at equilibrium, it's at any point. And oftentimes, this is measured using initial concentrations of reactants, which we're going to do a lot in electrochemistry. So again, just like K, the reaction quotient Q is solved by setting your product concentrations to their stoichiometric coefficient, or raised to their stoichiometric coefficient, over the reactant concentrations raised to their stoichiometric coefficient. Now, what does this tell us about the reaction? Well, if Q is less than K, we are not at equilibrium, and we are going to favor product formation. So as we look at this general reaction here, I'm going to have my equilibrium expression here, K, on the left, my reaction quotient here on the right. And just for the purposes of trying to better understand the reaction quotient and how it relates to the equilibrium constant, if I had a lot of product at equilibrium, then I would have a large K value. And if I measured my reaction quotient and it was less than K, that would indicate that I would have a lot of reactant at that time that I measured the concentrations. And so in order to achieve equilibrium, that means my reactants are going to turn into my products to reach that equilibrium level of concentrations. Conversely then, if Q is greater than K, the system again is not at equilibrium, and here the reactant formation is going to be favored. So again, for the purposes of better understanding the relationship between these two, if I had an equilibrium constant K that was small, that would imply that I had a lot of reactants at equilibrium and not a whole lot of products. And if I'm comparing Q to K and Q is larger than K at that time that I'm measuring the concentrations, then that would tell me that I've got a lot of product at that time, at that point that I measured Q. And so in order to achieve equilibrium, or when Q is greater than K, I'm going to push towards or favor the formation of those reactants so that I reach equilibrium. And then, of course, if Q is equal to K, you are already at equilibrium. So again, here's just a relationship showing you so here's just an expression showing you the relationship between Q and K. And if you've got a lot of, for example, a large K value and you've got a lot of product at equilibrium and Q matches that K value, well, that means that you are at equilibrium. And so when you measured those concentrations, they were essentially equivalent to the concentrations at equilibrium. All right, so we're going to run through this animation one more time, just sort of get equilibrium straight in your mind. Again, keep in mind this reversible reaction is the reaction between N2O4, which is a colorless gas, and NO2, which is a brown gas. So at the macroscopic level, you can sort of identify at equilibrium which of the two sides is favored, because you can tell based on the color. If it's colorless, obviously you're going to have more of your reactant concentration. If it's brown, you're going to have more of your product concentration. And we're going to start with, again, pure NO2. This time we're going to look, though, sort of at what happens with our equilibrium constant and how we can sort of calculate that and what that tells us about the reaction at equilibrium. So again, we start out with a lot of NO2, which is why macroscopically we start out nice and brown. As the reaction proceeds towards equilibrium, though, once we get to that sort of formation of each of them at a constant rate, recognize we're sort of a little more colorless here, indicating we've got more of the N2O4. And then when it comes to determining our equilibrium constant value, you simply need to look at the concentrations of your products and your reactants at equilibrium, plug them into your equilibrium expression, and when we do that in this instance, we get an equilibrium constant value of 4.63 times 10 to the negative 3. And again, a small K value implies the formation of reactants is favored at equilibrium. And indeed, we have a greater concentration of the N2O4 than we have of the NO2 when we're at equilibrium. And again, that K value, whether it's bigger than 1 or smaller than 1, is simply going to tell, or whether it is 1, is going to tell you, do you have a lot of product or do you have a lot of reactant?